started now. Everybody seems settled that's here. So today we've got 5 talks throughout the day. They'll be split again, applied maths, stats, applied maths, stats. So we're going to start off with some applied maths. I'd like to welcome Hoang Tran from Oak Ridge National Lab.
All right, thank you so much for introducing me, and thank you. I would like to thank the organizer for inviting me. It's really honor for me here. So today I'm going to talk about some results on recovery condition for compressed sensing applied to uncertainty quantification. So I would like to call that there is some gap when apply compressed sensing to uncertainty quantification, and we move toward it that direction. So this is the joint work with Clayton, Webster. I hope he's the end of the room. All right. So after the introduction, I will divide the talk into 2 topics. The first is some new condition for cross-Legendre approximation, and then the unified null space property for non-convex minimization. So for each part, I will discuss the challenge and the new thing we contribute into the problem. All right. So we interested in solving the parameterized PDE, which is a central object in uncertainty quantification. So we have the PDE, which is right at like LUY, which depend on Y is the vector of parameter, and the number of parameters may be very high. So this arises when we like parameterize the stochastic variable, for example, and we have Monte Carlo method to solve it. But if we want to exploit the smoothness which inherent in a lot of UQ application, it may be better to go for polynomial approximation, which feature faster conversion rate than Monte Carlo. So for polynomial approximation, we have some index set lambda corresponding to some polynomial subspace p lambda, and we find the projection of the solution, not projection, but approximation of the solution into that polynomial subspace. So the polynomial subspace formed by some fixed polynomial basis, orthonormal, and the unknown we have to find is C nu. And there's a lot example of polynomial approximation. So this polynomial may be Taylor polynomial, or orthonormal polynomial Legendre or Chebyshev. In that case, we have Galerkin method, or interpolation is really square. And today I'm going to focus on compressed sensing. Okay. Let me discuss a little bit about the strategy to choose the index set. So the choice of index set is very important in polynomial approximation, because with a choice of index set phi, the best solution we have, the best approximation we have is the projection of the solution into that polynomial subspace. So if we choose a good index set, we can have the good approximation. But if we choose not a good index set, even when we project the solution into that subspace, that projection may be very far from the true solution. So the standard approach imposes the index set a priori. And here there is some example: tensor product, total degree, hyperbolic cross, and Fumolia. And we can add some like anisotropy here if we know which direction is more important than like another direction. But standard approach imposes the index set a priori. Okay. So what would we decide what in the ideal world? So we like to find an optimal index set. which produce the approximation that is closest to the true solution. So, or more rigorously, we find an index set, I call it lambda s best, such that the error of the true solution or the projection of the solution to the subspace is modest. For an example, if we measure the error using L infinitive norm, we can apply the triangle inequality to bound this norm by the sum of the coefficient. Yes.
What is y then? Sub y.
Oh, sub y.
Y. Yeah.
Oh, y. So y is the parameter.
Okay.
So the solution u is a function that depends on several parameters. Other parameter. Yes. So if we bound it this way, then one strategy is to choose the index set s lambda s best corresponding to largest coefficient, so that the residual, the coefficient that remain that left is smallest. But the challenge is that to find the largest coefficient, we need to compute all of the coefficient. Pick the largest one, and so it is not feasible. So in the following, I will denote lambda s u is the best S-term error. Because the best S-term is not feasible, so we want to find some method that can produce some approximation that is close to best S-term. So compressed sensing provides us a tool to do that. It is the method that first developed for signal processing. So compressed sensing is around solving for a sparse signal. So the signal here, we have a the length is long, but only the color here is non-zero. Okay. So this signal is sparse, and we try to recover the signal using the underdetermined system. So we have the fat matrix here. This linear system have less data than the unknown. Now, under the sparsity assumption, mean only a few coordinates is non-zero, we can reconstruct the signal using some sparsity induced norm. We can use L0 norm to find the sparsity solution of this system. But even better, we use L1 norm, and that is the reason, I believe that is the reason why compressed sensing is so successful, because it can find the sparsest signal based on the convex minimization, which is easy to implement. Okay, so how do we hope, and what can we hope to apply, successfully apply compressed sensing to polynomial approximation? There is something similar in case of signal processing. First, if we consider a smooth function u on some domain big U. So in uncertainty quantification, we have more likely we have less data than desired. So because each measurement is expensive, so we have limited amount of data. We have the coefficient decay fast. So in that case, the unknown, the vector of unknown C nu is not exactly sparse in the strict sense, but approximately sparse, means that it decays fast and only a few, a small percentage is non-negligible. But we don't know the shape of the correct index set. So if we apply the compressed sensing approach here, we can start with the big index set, not necessarily the optimal index set. We start by something big, and that relaxed for us from choosing a very good set from the beginning. And the thing is that in compressed sensing, we're solving under the determined system, means that we don't need to solve the system with the number of equation is at the same size of the size of the index set. So that's how we can choose the not optimal index set at the beginning. So let me put it together. So we start by some set lambda 0 with n multi-indexes, maybe far from optimal, and our goal is to find approximation of u written in this form, comparable to the best estimate approximation. And I want to use the number of measurement which is far less than n, and hopefully scale linearly with s. Okay, so the compact sensing, we randomly sample the point, and we form the matrix. We call it the sampling matrix. So each column of the matrix corresponding to one basis, and each row of the matrix corresponding to the value of the polynomial at one sample point. Because we have less sample point than the number of bases, so this is a fat matrix. And the coefficient C is the solution of the underdimensional system. So I write U is approximate size C because this is not the strictly equal, because the U is represented as the infinite sum of this term, and I truncate by the big set lambda, so there's still some term left. So it's just approximate. And so if I see as a Sprossy solution of this equation using the compact sensing approach, like L1 minimization and subject to this condition. So eta is based on the truncation error. Okay, let me discuss a few more terms and tools. So we have uniform recovery versus non-uniform recovery. And from now, instead of use psi, I will use notation A is just a normalized version of psi. Yeah, just so that you know that I jump the notation from psi to A, but this is just a technical detail. The non-uniform recovery is so first, because compact sensing generate the sampling matrix randomly, so the recovery always come up with some probability. And the non-uniform recovery means that the recovery is success with high probability for each S sparse vector. And the uniform recovery is that you generate some random matrix, and you hope quantify the condition of that matrix such that that matrix is successfully reconstruct all of the S sparse vector. So this is non-uniform recovery, and uniform recovery is using two different set of tools, and so our work focus concerned with mainly uniform recovery. Okay, so this is the path to establish the uniform recovery. So to find the uniform recovery, we need to find the prove the null space property. And in most of the case, null space property is equivalent to the uniform recovery. But the null space property does not allow us to quantify the number of samples, the amount of data we need. So we need something else. We need the RIP, restricted isometry property. And the restricted isometry property, it allows us to quantify the number of samples that we need to guarantee the recovery. So restricted isometry property, it says that I satisfy this RIP if it acts like isometry for every S sparse vector. So for every S sparse vector, as spark vector the norm of AZ like approximate the norm of Z. And the intuition here is that A needs to satisfy these conditions, so the kernel of A does not contain any non-zero S spark vector. Because if the kernel of A contains some S spark vector, and the solution, so if a spark vector is a solution, then the sum of that vector with the non-zero S spark vector in kernel of A is also another solution. So we have two spark solutions. And whatever, in that case, whatever method you use, then I believe we cannot reconstruct the unique true solution. A satisfies the null space property of order F if the kernel of A belongs in this set. So similarly, we don't want the kernel of A is very big. And the compressed setting reconstruction is quantified in terms of best estimate approximation. So when we say the solution of the compressed sensing is comparable to best estimate, which is mean that the error is bounded by the best estimate, error multiplied by a constant. So now to quantify, to prove the necessary number of measurements we need to get some recovery, we need to find the number of measurements so that the RIP is satisfied. So we define the uniform bound of the autonomous system, the subnorm over all of the index set, over all of the index in the chosen index set of the polynomial subspace, or of the polynomial basis. So this is a quite classical theorem. In we have psi is the random sampling matrix. If the number of measures bigger than k square, this k times s times log factor, then A satisfies RIP with high probability. So let's look closer at this estimate. So we have log n is the size of the polynomial subspace. It is not a trouble here because n only appears in log. S is good, the fairly linear in S. But the term k may be a trouble, particularly in polynomial approximation and in UQ approximation, in UQ application. So many metric and signal processing, Fourier, Hadamard, and circular, we have k is 1. For polynomial approximation, particularly in high dimension, k can be very high. So example is Chebyshev basis, k scale 2 to the d over 2. And the Legendre basis, k is bigger than, I think it should be square root of n. Yeah. So k square bigger than n, and which means that estimate doesn't really meaningful because we need number of samples bigger than the size of the polynomial subspace. There's a few ways to deal with high k. Let me start with an example of Legendre approximation. I mean the bounded domain. So in the bounded domain, the most natural sampling strategy is a uniform sampling. If you use the uniform sampling, you come up with the Legendre approximation because Legendre polynomial is autonomous in uniform sampling. And the number of measurements for Legendre polynomial, the minimum number of measurements for Legendre polynomial reconstruction doesn't exist as far as I know, because as we see here, k square bigger than n, mean that m bigger than n. So there's some way to overcome it. The first way is by this set of methods. They have the same philosophy and they follow by several authors. And so in some they are mentioned that reconditioning or coherent optimal sampling, Christopher sampling. So the idea here is that, so you have the matrix A and you have K is big, but the K is big only on a few row, or it is really concentrate on some row, and you want K is more spread out, so that you mean the magnitude of the row be more spread out, so that you can reduce K. In that case, what you can do is you multiply by some preconditional, some matrix. So this is called preconditioning matrix. So this preconditioning matrix is a diagonal matrix. And when you multiply it, here it means that you multiply each row of the matrix A with a weight, and the row with bigger subnorm you multiply by a smaller weight. You penalize more. And the row with smaller subnorm you multiply by bigger weight. To make the subnorm, the weight is more spread out. Yes.
Do you change the sampling method, or do you just wait?
Oh yes, that is a good question. Because I wait, then I need to change the sampling matrix, because the matrix PA does not orthogonal with the original measure anymore.
So the weight depends on the probability of inclusion depends in some sense on the weight. Or how do you change the sampling?
Well, from the beginning, with the original matrix, I have some sampling distribution such that A is orthogonal. And when I multiply this preconditioning matrix, then for most of the case, I believe that we know the sampling strategy, explicitly. If we don't know, then some people apply some method like MCMC to generate the sample point. Yeah. Okay. So the preconditioned. Okay. So we have Legendre polynomial. We can precondition Legendre to get something better. So we got preconditioned Legendre polynomial with Chebyshev sampling, and we reduce K from n to 2d over 2. Another strategy is the weighted minimization. So the weighted minimization base is on the idea that for the smooth function, the smooth solution, the big coefficient is likely have low index, concentrate around the origin. But in which direction we don't know, but concentrate around the origin. So instead of trying to recover the best S term, we can recover the lower best S term, which is the best approximation which has support on the lower set. And the lower set is, heuristically, it is the set without a hole. The set around the origin, and that does not hold. So, the way this L1 minimization developed by several authors, including one paper of ourselves. And so the key contribution in that paper is we found out if we a choice of the way that works particularly well. So if we choose a way by this way, we can quantify the gain, or we can get in terms of number of samples. So we solve this problem with the same penalty term, but we add the weight here with this way. So here we have the number of samples. So here is a fast, quick compare between the weighted and the unweighted L1. So for the weighted L1, if we use Chebyshev basis, we got S log 3 over log 2 versus log S square in unweighted, or S square in Legendre basis compared to S log 3 over log 2 plus 1 for Legendre basis. So we get something in terms of number of samples. And this is also some example that shows. So the weighted without choice way is the red line, which we found consistently better than unweighted in every numerical test, and it is very competitive with the other choice of weight. So on the left and middle panel, we see the sparsity of the solution of this test function. Okay, so that's quite a long introduction. I hope I persuade you that the term K is very important in both analysis of complexity and algorithm development. So I would like to come back to this slide. Okay, see that. Okay, so far there's no recovery guarantee for Legendre polynomial if we rely on this estimate. So the first topic I want to discuss is that we find another way to develop to prove the guarantee condition for Legendre expansion without using this estimate. So here is some simple test. If we use this estimate and K is, so then for Legendre system to have K bigger than or equal to square root of 2n plus 1. So K is really depend on not only the size of the matrix but the maximum degree of the polynomial in the polynomial subspace. So I try with two different subspace with the same size, but the maximum degree is different. The first one, the maximum is 200, 500, and 2000. So correspondingly, K is gonna be square root of 401, 500, I'm sorry, 1001, and so on. Okay, so if this estimate is sharp, then what we expect to see is that the recovery rate is better for the purple line and worse for the red line, but we didn't see it here. So the number of sample here is likely not really depend on this term. And even though Legendre polynomial is not the best polynomial basis for bounded domain, but there's still some successful recovery rate for Legendre polynomial. So our goal is we want to find a new estimate on the mode measurement which does not depend on K. So instead of depend on K, which is this red line, we find an estimate depend on the envelope bound of all of the system, which is this line. So if we rely on this red line, whenever we change the subspace, then this line may be changed. But it is uniformly bound for whatever polynomial subspace that we choose. So this is our main result. For this one, you got m bigger than or equal to s squared times log factor. From d bigger than 1, you got m over log to the 4d of m bigger than s squared. And we discussed this estimate more detail later. Okay, so to work with an unbounded system, it is very hard to prove this side of the RIP, but luckily there is another related condition, which is why not quite popular at RIP, but surprisingly really helpful for us this time. So we have received eigenvalue condition, which only require the bounded from below of matrix A. So for every Z in this set, so this set is a set, this set C S alpha contain all of the S-Fox vector, but a set a little bit bigger than the set of S-Fox vector. So for every z in this set, we have this bound from below. And this is really, I believe that this condition is really stronger than RIP in the sense that for many matrices, random Gaussian and sub-Gaussian design matrices, REC satisfied, but RIP does not satisfy. And the good thing about REC, so first we have the REC also imply the null space property. So for the diagram, we have the number of sample imply the RIP, imply null space property, then imply uniform recovery. So here we have REC imply null space property and consequently uniform recovery. All right. So now our task is to quantify the sample complexity that satisfy the REC. So we define the function psi, this one, so y is the parameter, and z is the, let me see, a vector in Cn, yes. And Es alpha is the set of basically the set some convex whole of the set of S-Fox vector which L2 radius is 1. So this condition, I'm sorry, this inequality equivalent to this inequality. So there's nothing fancy here. I just use the new notation and write the REC property in this new notation. Okay, so the path is that to prove this inequality, I use some requisitization. So I would like to mention that so this idea come along from all the papers which start by Bogan and then Habib and Regep, and in the paper of weighted L1 we extended idea for general bounded autonomous system, and the original goal is to reduce the log factor by 1 unit, but then we see that there's some other nice thing come up which help us to do with the Sparks-Legendre polynomial. So we construct, we discretize this mapping site to very many small cells. Each cell is the indicator function. And then we, because that function psi here is very simple, so we can use some basic tail estimate like Chernoff bound or Bernstein bound to estimate this inequality, but for each cell with high probability. And then we need to use a union bound. But to use a union bound, to make this from this, we need the number of the cell is not very big. We need to design a cell in some clever way. Okay, and we have to count the number of all of the cells. All right. So here, if you're in the business, then the way to count the number of cells is quite standard. So we use a Murray empirical method, and we relate that with the covering number of this set. So this set is like the convex whole of L1 of S-Fox vector. Union, intersect with L2 ball. So we find the covering number of this set under this matrix, and the covering number itself is involved in the upper bound of the expectation of the distance function. So the distance function is bound by this thing. So all of this thing is quite standard. And here is the idea that we have. So instead of bound this quantity theta y I, we can bound it using the subnorm and get this bound. If we use this way, then the condition m bigger than k square times s come up. But if we bound using the envelope bound, I mean, of course, we cannot find a bound that is true for every set of sample because it is unbounded. But when you generate a set of sample, it is very likely that this quantity is small, and with a very small probability that this set is that this quantity is big. And in that case, you can bound with high probability this expectation of the distance less than this term. Okay. And then I call the set of sample that make this quantity small is the preferable set because it makes this term smaller. And consequently, I come up with the number of sample bigger than s squared times log factor. I think this is in 1D case. In multidimensional case, because we have the term log d minus 1 here, so we have to divide m by log of 4d. Okay. Okay, so let's collect things together and come up with the theorem. So if m bigger than s squared times log 4d m, then REC is satisfied. All right. And then we got the reconstruction. The error is that the best estimate error multiplied by plus the term involving the noise. Okay. So let me comment about this bound a little bit. So in 1D, I believe that this bound is optimal. In terms that the number of samples we need then is m bigger than s squared. And it is also the number of samples that the discrete least square would require. And there also a recent paper by this author Ben Adcock, Platt and Sadrin say that if you generate a sample uniformly and you want a stable approximation, then you need the number of samples quadratically with the size of the polynomial subspace. In multidimensional, I believe that we need to pay something for the dimension. And I'm kind of believe that so this is the price we have to pay. Maybe the number 4 here, I think that this is the artifact of analysis. But yeah, there must be some dependent on the dimension, which it also happen like in the case when we analyze there's some result on like approximate like cogomorph and width, and when we go up into the dimension, then this log term the power the dimension also show up. So I think maybe the situation up here, but that is just some this is just my guess. Okay. So this is the numerical illustration about the preferable set. So the preferable set is the sample set that make this bound small. So in this example, I will show that okay, this is really help to reduce the error and push up the successful rate. So I generate 1,000 sample set, and I divide into 4 subsets ranked by the increasing order of this quantity. Okay. So what I observe is the set of the set of sample set that have the smallest bound that I just mentioned have the smallest error and the biggest successful rate. Okay. So if I try to, so in this experiment I try to reconstruct the signal of sparsity 14 and let's use the 1500 sample set. Now I just quantify the error of the sample set in the first quadrant. I'm sorry. So this should be, yeah, first part. This part, which have the smallest bound. Then I got better conversion rate and better recovery rate. And this is a error rate corresponding to the worst sample set. So it really have a little bit. This is the same plot, but here I fix the number of sample and try to vary the sparsity. Okay. Yeah. So for the second part, I will discuss some null space property for non-convex minimization. So non-convex minimization now I think is increasingly using in uncertainty quantification application because the reason is so for the non-convex regularization you have some, if you look at this ball, it is closer than L0 ball than L1 ball. So hopefully it gets you the sparser solution, or it requires less number of measurements. If you can afford to pay for the extra computational cost to solve a non-convex program. So there's a lot of non-convex regularization that is introduced and tested in uncertainty quantification and other applications like signal processing. So LP norm is pretty popular, L1 minus L2. I think pretty recent, cap L1 to two-level L1, sort L1, transform and scat. This is in statistics, I think. So this is some extra plot for the ball of the L's for the non-convex minimization that I showed in the previous slide. So the idea is that you have the ball is closer to the L0 ball than L1 ball. All right, so there are several papers, several authors that show non-convex minimization is better than the L1 in practice. But there's something lacking in the theory. So the theoretical uniform recovery guarantee is established in, again, restricted isometry property. In some case, it is better than L1. In some other cases, it is more restricted than L1, and for some case, it is not available. So my goal is that, okay, so first I want to discuss the diagram. So when I look, when we look at this method and see the number of samples they require is bigger than the number of samples for L1, it confuses us a little bit But then we figure out the problem is that for this method, the author starts from some null space property which is more restricted than the null space property for L1. So if the null space property is more restricted than the null space property for L1, then whatever tool, whatever method you use to in this part and this part, it doesn't really help, because you need some sufficient condition to prove something stronger than null space property for L1. Okay, so in this part, I will present some results that verify that non-convex minimization is better than L1, and that is based on some variant of null space property, similar to L1 or less demanding than L1. Okay, so the generic assumption I have is the penalty is concave, symmetric, mean that you can do the whatever permutation and got the same value, and separable or not separable. So I divide the analysis in two cases: separable and non-separable. Separable means the function in Rn can be written as the sum of the function in our and function in R1. Okay, so this is some example of the existing result. So for example, in two-level L1, currently the requirement is that the kernel of A belongs to this set. And L1 minus L2, currently the kernel of A belongs to this set. And if you look carefully, this set and this set is strictly subset of N in L1. So it means that this requires the kernel of A belong to a smaller set, more restrictive than kernel of A. Okay, so first for the case of I think non-separable. We prove that the null space property is sufficient, and in some case, some weaker property is also sufficient. So here we replace the less than, strictly less than by less than or equal to. So the basic idea is we define two sets, right? And we want to prove that the kernel of A belongs to K1 of the kernel of A belongs to K2. So our goal is just show that. So for every V in K1 or K2, I got the penalty applied to X strictly less than the penalty applied to X plus K1 X plus V, and then I'm done. Okay, so the proof based on the tool in majorization. So I want to prove Rx less than Rx plus V. So with this condition and this condition, you can imagine that X plus V is more spread out than X. And if it's more spread out than X, so you can use this result. Sorry, I think it is in So for two vectors of the same sum, the vector that is more spread out, when we apply the penalty, you're gonna have the smaller value. The penalty applied to the more spread out signal gonna be smaller, because the penalty satisfies the condition that I just hold here, which is symmetric and concave. Yeah, and then there's some other technical, but I believe that is the main thing. Okay, so to summarize, in this case, you have the symmetric and concave penalty is at least as good as L1. For the separable, I believe that the proof is easier, but you have some stronger condition. You only need stronger condition mean weaker, less demanding property. So you only need the kernel of A belong to this set, and this set is strictly bigger than the set corresponding set. I mean this set. If the penalty is concave and separable. Okay, so some concluding remark. I discussed two recovery conditions that I hope fill some gap in current compressed sensing theory, which include the recovery guarantee for sparse Legendre approximation and some new property involving non-convex minimization. So to conclude, compressed sensing is I believe in a powerful approach to reconstruct the sparse signal. If we can afford for the L1 minimization. Yes. Thanks.
Okay, thank you. Great timekeeper, thank you. So has anyone got questions?
Yes.
So I'm going to make a small speech about statistics, if you don't mind.
Okay.
So most of your statements are with respect to the randomization.
Yes.
They're probabilistic statements.
Yes.
Right. So in statistics, we stopped using randomization theory about 30 years ago for our decision making.
Okay.
So what about using a deterministic sequence rather than a random? Because if you randomize, then if you can have a value close to the previous value.
Yeah.
You can get clustering. Why don't you use a sub-bold sequence or some space filling?
Oh, so you're asking about the
That would be much
deterministic sequence in generation
Yes,
the sample point.
And forget about the randomization and make some other statement about bias or discrepancy or something.
Yeah, I agree. So I believe that one limitation of compressed sensing is that the tool and the method is really depend on the random sampling. So for the deterministic sampling, I think some author already tried that. But one challenge is that they call, I think, quadratic bottleneck. If you use a deterministic sampling, then the best you can get so far is that the number of samples is dependent not linearly but quadratically in the sparsity.
You see, just to follow up, the sample size in statistics is really, in some sense, not as important as the location of where you actually put
Yes.
the thing. So you've got this balancing act. I mean, forget about the sample size and make sure that you're weighting your randomization in some way, as you have. You'd call them selected samples or something. So that's got in then that in statistics is called optimal experimental design, and that has a 50-year-old history. So
Okay.
so maybe we us guys should get together and use some of the statistical methods of optimal experimental design with the compressed sensing. So I've been speaking to people about it.
Okay. Yeah.
And the end of speech.
Okay.
Great. Anybody
Yeah,
else?
thanks.
Any questions? None at all? Right. Okay, so thank you, Henry, for suggesting a way we can work together. That's great. And thank you, finally, for your talk. Thank you.
Okay. Thank you.